sí, yo aquí estoy. Sí, yo aquí estoy todo el tiempo. Cualquier cosa le llamo.
Yo creo que sí, sí, porque por lo menos una o dos. Doctor, ¿van a estar todos al mismo tiempo aquí? ¿Van a estar todos al mismo tiempo?
No, yo creo que al final se sientan todos.
Ok, solo al final.
Sí. Ahorita,
Sí, yo creo que
probablemente, sí.
es que están amontonadas.
Sí, que os usen el podio, probablemente. Sí, yo creo, sí.
Ajá, okay.
Sí. Le vamos a dar 3 minutos más.
Sí, sí.
Pues así para las 10:15.
Que lleguen un poco más, ¿no?
Sí. Yo creo que sí.
Ya empezó la transmisión. ¿La transmisión?
Ya. Correcto. Sí.
Juan.
A continuación se darán unas breves indicaciones sobre medidas de emergencia ante alguna eventualidad en este recinto. Usted se encuentra en el auditorio José Luis Sánchez Briviesca, ubicado en el sótano de la Torre de Ingeniería. En caso de emergencia, le suplicamos que mantenga la calma y, de ser necesario, desaloje el salón de manera ordenada. Siga los señalamientos de evacuación que se encuentran ubicados en los pasillos laterales con dirección al lobby. Las puertas de emergencia están ubicadas al lado izquierdo y derecho de los elevadores y abren hacia afuera con la barra de pánico. Solo deben abrirse en caso de emergencia. Si llegara a ocurrir un incendio, el salón cuenta con 4 extintores, 2 al frente y 2 a las salidas, y las alarmas se encuentran en los pasillos laterales. Durante el desalojo del inmueble, el personal de la Comisión Local de Seguridad de la Torre de Ingeniería dará las indicaciones pertinentes. El punto de reunión se encuentra localizado en la explanada Oriente, saliendo por las puertas de emergencia de frente. Les recordamos que no está permitido el ingreso de bebidas y alimentos al auditorio y está estrictamente prohibido fumar. Esperamos que disfruten su estancia.
Muy buenos días a todos. Es para mí un gran placer moderar una reunión con el objetivo que puede ser tan importante para la actividad de muchos de los que estamos aquí en el futuro cercano. En esta ocasión tomamos la oportunidad de la presencia de un gran número de personalidades del país y fuera de él que puedan dirigirse a nuestra comunidad y expresarnos básicamente cuál debería de ser o cuál es lo que pensamos es el futuro de la ingeniería sísmica, qué es lo que debemos nosotros corregir de eso que se piensa debe de ser el futuro de la ingeniería sísmica y finalmente hacer un llamado para que mucho de nuestro esfuerzo finalmente tenga como objetivo el beneficio de la gente a través de una llamada resiliencia de nuestras comunidades. Todo este evento estará ampliamente difundido en redes sociales. El motivo de lo reducido del arreglo es la necesidad de poder utilizar la presencia de nuestros visitantes que graciosamente han aceptado venir a participar en el Congreso Nacional de Ingeniería Sísmica. No podíamos obviar esa oportunidad para iniciar algo que es muy, muy importante, que son los 70 años de existencia de este Instituto de Ingeniería. Le cedo la palabra a nuestra secretaria académica, quien en representación de nuestra directora, la doctora Rosa María Ramírez Zamora, nos dirigirá una palabra. Nuestra secretaria, la doctora Norma Patricia López Acosta, nos dará la bienvenida. Muchas gracias.
Muchas gracias, doctora Ayala, gracias por esta invitación. Y efectivamente, en nombre de la directora del Instituto de Ingeniería, me es muy grato darles el día de hoy la más cordial bienvenida a todos ustedes, particularmente visitantes del extranjero, como bien lo menciona el doctor Ayala, a este evento que es un panel titulado Retos y oportunidades en el futuro de la ingeniería sísmica hacia una resiliencia comunitaria más incluyente. Tiene como moderador precisamente al doctor Gustavo Ayala, un investigador consolidado de nuestro Instituto de Ingeniería. Y también expositores de renombre que yo veo vienen de distintos países, incluso de Europa y también de Estados Unidos. Y por supuesto, investigadores reconocidos de nuestro país también, ¿no? Me es muy grato mencionar el día de hoy y saludo muy cordialmente en nombre de la directora del Instituto de Ingeniería y en nombre propio al doctor Luis Esteva Maraboto, que nos acompaña el día de hoy aquí en este panel. Es un gran orgullo estar el día de hoy aquí con el doctor Luis Esteva. Él es un investigador emérito del Instituto de Ingeniería. Muchísimas gracias, doctor, por estar aquí. Gracias. Saludo también con gusto a varios de los asistentes panelistas que estarán participando en este panel académico. Andrea Prota, de Italia, Mario Ordaz, por supuesto, otro investigador del Instituto de Ingeniería, Artur Pinto, del Laboratorio Europeo de Evaluación Estructural, Arturo Tena Colunga, de la UAM en Azcapotzalco, aquí en la Ciudad de México, Khalid Mosalam, de la Universidad de Berkeley, Lars Abrahamczyk, espero pronunciarlo bien, de la Universidad de Weimar, José Manuel Jara Guerrero, de la Universidad Michoacana de San Nicolás de Hidalgo, Guido Camata, de la Universidad de Annunzio Scieti Pescara, de Italia también. Muchísimas gracias. Me da mucho gusto darles la bienvenida aquí en nuestra universidad y sean ustedes, siéntanse cómodos como en casa, incluso si quieren visitar algunos de los laboratorios del instituto, creo que se pueden acercar a cualquiera y si tienen oportunidad pueden hacerlo también. Es un panel intenso de varias horas, de 11 a 2 de la tarde. No me queda duda que será un referente de discusiones en los avances en cuanto al futuro de la ingeniería geotécnica. Supongo que, bueno, no supongo, estarán abordando temas de relevancia sobre retos y oportunidades de todo lo que tiene que ver con la ingeniería sísmica, y seguramente tendrán discusiones bastante intensas e interesantes aquí en este panel, y que seguramente para los asistentes, supongo que hay varios estudiantes, pero también personal de la práctica de la ingeniería estructural. El evento se está transmitiendo en línea, es un evento híbrido, tenemos una importante asistencia aquí físicamente en este auditorio, pero también entiendo se está transmitiendo en línea. A todos ellos, muchísimas gracias. Estas discusiones seguramente les van a proveer de conocimientos muy valiosos a todos los que están siguiendo este evento. Y pues bueno, reitero mi agradecimiento al doctor Gustavo Ayala por organizar estos eventos académicos que son de gran valía para toda la comunidad académica del Instituto de Ingeniería, pero también en nuestro país y a nivel internacional. Muchísimas gracias, doctor Ayala, por realizar esta labor. Y pues bueno, les dejo en este panel Retos y oportunidades en el futuro de la ingeniería sísmica hacia una resiliencia comunitaria más incluyente. Les deseo las mejor de las jornadas y mucho éxito el día de hoy. Muchísimas gracias. Buen día a todos.
Sí. Muchas gracias, doctora, muchas gracias. Pues le agradecemos mucho su presencia. Y if you allow me, I would like to shift to English for the benefit of our guests and also for the benefit of those that are watching us through the social networks. And then I would like to say a few words about this institute and why 70 years are important. 70 years matter. It was in 1955 when a small group of visionary engineers in the School of Engineering and the engineering companies decided in the right moment for Mexico, when Mexico was building all its infrastructure, to have a research group in which this infrastructure could be supported with research activities. These 70 years have led us to have very many things that have been very good for this country. And we would very much like to continue doing this. And one of the main reasons why we are organizing this type of events is that they know, the people outside and around the world know that we are still here. And we are still here working very, very seriously and doing our best of efforts to consolidate the knowledge of earthquake engineering on the benefit of the people. Then I would very much like to thank all the participants in this event that took the time of first coming to Mexico, which is not an easy thing, to bear with the traffic, which is even a worse thing, and escaping from their main reasons why they came to Mexico, that was to participate in the National Congress in Earthquake Engineering, to come to us and give us their opinion about basically three different but very related aspects. Their opinion about what they think civil engineering research is going to at this moment, what they think it should be going, and concluding to tell us what we have to do to move the interest to the benefit of the people. So this is something that would be very, very important for this institute and the next activities that we will develop during the next year to celebrating the 70 years of this institute. This time, and I must say, I am very happy, I'm very honored that our mentor, one of those that initiated our institute, could come to see us, to meet us, and to tell us what he thinks. We are very interested to know, to hear from him, from somebody that knows the reason why this institute was created, the reason why we are here to keep working for a better Mexico and for a better world. So, Luis, thank you very much for joining us. And as we go along, I will introduce the participants, and leaving the very end of the meeting a moment for those attending via the social networks and here to give us some questions about what they're going to talk about. So for this, we will start with our mentor. We're going to show the presentation of Professor Esteva, and we thank our secretary to have been here. And I know you have many occupations, then, all right. Thank you very much.
Thank you, doctor, and you are very welcome. Thank you very much.
So, muchas gracias. Le agradezco mucho. Ándale, que le vaya muy bien. ¿Nos podrían proyectar la presentación del doctor Esteva, por favor? ¿Cómo que no la tiene? Ay, Dios mío. ¿Qué? Well, bueno, para continuar mientras traen la presentación. La tiene Amalia. No, Amalia la filmó. Bueno, no, comenzamos, véame por favor eso. Y comenzamos entonces, voy a pedir al siguiente expositor que por favor pase, será el profesor Andrea Prota. Por favor, Andrea. Yeah, please do come here. Well, it's my pleasure to introduce to you Andrea Prota, professor of Università Federico II in Napoli, and president of the Return Foundation, an European initiative for Italy, dealing more or less in the same idea that I mentioned before. Yeah, what things, what we could do, and what it should be, what we do to protect the resilience of our communities. Andrea Prota is a prominent professor in this university, and as I mentioned to you, president of the Return Foundation, and initiative that will be finished at the end of this month, and that has such a massive amount of information that more or less will be the basis of what we aim in this meeting. You know, there's so much information of what is being done, what it should be done, and how all this could affect resilience. So, Andrea, thank you very much for coming and for being here with us.
Thank you. Thank you, Professor Ayala. Thank you, Gustavo. My greetings to Professor Esteva and to all colleagues in the room and all people that is watching online. So the moderator has given us 15 minutes, so sometimes I will look at my phone because we need to stick to the timing. So I tried to put together some slides to address mainly the questions that Professor Ayala was mentioning. And I would like to recognize that in the preparation of these slides, I worked with my colleague Maria Polese. That's why I thought it was fair to have also her name on the slides. How can I move? Excuse me. How can I? Thank you. And in trying to address the topic of this roundtable, I will make some reference to two main entities. So I put also the web address because we have a short time, and so in case you want, you can check out the information on the web. One is ReLuis. ReLuis is a network of earthquake engineering laboratories in Italy. It was born just 20 years ago and is a center of competence of the Italian civil protection. In ReLuis, we mainly work as earthquake engineers. And then Return, Professor Ayala already mentioned. You see the acronym is Return, stands by Multi-Risk Science for Resilient Communities Under a Changing Climate. This was a project funded under the Plan for Recovery and Resilience in the topic of risks, natural, environmental, and man-made risk, large funding, 115 million of euros for 3 years, involvement of about 1,000 researchers, many entities, private and public. And so I would say that ReLuis was born about 20 years ago. Now here we are celebrating the 70th of this institute, but ReLuis is more let's say, the traditional earthquake engineering studies. Return is, I think, a modern step forward because the competencies we have in Return are about 50% what we call hard science, so engineering, architecture, geologists, biologists, mathematicians, and then a strong part of social science, which I think will be useful to address the third question that Gustavo was mentioning. Just a very quick reference about the Italian system, because we have a National Civil Protection Service, and the role of universities at service of the country is regulated by the Civil Protection Code, which was issued in 2018. So it's very clear the recognition of the role of a scientific community as support to civil protection activities and also for collaboration between scientists and civil protection decision makers. So in this sense, in our country, there is a strong correlation between science and government. About seismic reduction, with ReLuis, we play on disaster risk reduction on the three components: on the response, especially after the events, on risk analysis, and I will mention something later with the several projects, and also on mitigation and capacity building, which is a lot of activities devoted to the awareness of people, provide design guidelines and also information practitioners. When I was coming here, I saw that probably in this table there is someone who developed seismic risk maps a few years ago. And within the ReLewis, we work on this. As a support of the civil protection, we worked for the National Risk Assessment, the 2018. And as ReLewis, we developed the National seismic risk map. You see some maps for different damage state on the right-hand side. And we know this is important for resilience. So I think resilience is something that allows us to look at what we already do since many years, but putting them all this together and having the perspective of resilience. So for sure, the seismic risk maps are important, and in order to build them, we need some ingredients. And that's why, for example, we performed in Italy, I was very much involved, we performed a lot of work on the inventory. So we made intervention-based protocols and we made surveys about the typologies of buildings in different municipalities. You see, as of now, we have covered more than 500 municipalities surveyed. So this means that we have an idea about the structural configuration of buildings, residential buildings, school buildings, and so forth. And we know this is very important because in this way we can really make a reliable assessment of risk. As I said, not only residential but also schools. I just need to go fast. You see more than 1,000 schools. So we also know very important information about the school. And on the mitigation, I wanted to share with you interesting outcomes of a project about the definition of criteria and solution for the design of integrated and sustainable interventions in Italy, but I think all over the world. We have a strong pressure in order to reduce the risk, the seismic risk, but at the same time to reduce the energy dispersion of buildings. And so the effort we are performing is to push the government, but also the industrial world, the practitioner, to look at this problem together. So once you open up some works on a building, to take care of both the seismic part and the energy part. And so in the book you see, you can access by the QR code, there are also examples which are important for us, and civil protection wants us to develop practical examples because all these should reach the practitioners, the engineers, the architects, the real world. And that's why research becomes a support. I wanted to mention also some interesting activities we are doing on the use of satellite data for integration of monitoring for buildings and bridges. I can just go very fast on this, but this is a very important potential. Again, to have a survey and to understand, to assess the eventually displacement of bridges or displacement of buildings and establish priorities for interventions. So on this I go fast. And let's go on the second part because time is short. Resilience. Okay, we know that we need resilience is a tool, I think, that can allow us to move from strategies to solutions and then to action. And to answer, of course, this is my point of view, the question, I think we need to improve from one side the support of government because science should be translated really in policies in order to have really disaster risk governance. We, of course, in order to do this, we need that governments assure money, so financial support, and we need to involve and support the stakeholders, which are practitioners, entities like local authorities, but also civil society. We know that about resilience, there are different definitions. I just have a couple of slides, I just go fast. But these slides allow me to stress the fact that in order to have a good disaster risk governance, this is not necessary to have good earthquake engineering, but we need to interact with who is preparing the laws, who is designing the policies, and we need to explain the responsibilities that each component of this process has. So you see learning, resource and capabilities and actions. In these slides you find one of the way of defining resilience. I just leave it like that. That's a definition in terms of terminology from the Disaster Risk Reduction of United Nations. But in any way, resilience is aiming at recovering from the effect of an hazard in a timely and efficient manner. We know that there is also this proposal of definition from MCIR, the American Center for Earthquake Engineering Research, and you see this circle that allow us to stress the fact that the resilience has different dimensions, and also that we need to put together risk assessment, resilience assessment in an holistic approach, and we need to understand how to measure resilience for different domains. This is a typical slide about resilience. I just left this for all of you that are in the room or online, but I just say on this slide that we look at the community functionality, which is an aggregation of different functionalities which are related to facilities, to lifelines, and other components of the built environment and of the social components of our society. Something we are doing in return, just to share with you, in this flowchart, when we try to measure disaster resilience based on functionality, we have an initial functionality, then we have a functionality of the system, the social system, interested by the hazard, which has a drop, aftershock, and then we need to evaluate the recovery pattern over time. And then, for example, in return, we are working a lot on building portfolio recovery under earthquake, because we know that those are defined impeding factors. So some factors that can cause delay. Which are these factors? The lack of money, the lack of workers, the lack of a good policy. And so you see that curve functionality over time can have a delay and then a trend which depends on this. And we are doing on this, creating different scenarios. Another concept, I think, and I hope that we all agree, risk and resilience should be looked at as a progressive update. So we start to measuring resilience, but then we need to understand that as we perform interventions or something outside changes, resilience changes, and also the risk should be updated. I just a few more minutes and I'm done to answer the last question, and also to share with you what is a very strong belief that I have, but that we have developed in Italy. We have understood that in order for our science to become useful to the community, you were saying to Mexico and to the citizens, we really need to link with people, to the community. And so we need the stakeholder involvement at different levels, the local government authorities, the policy makers, the community groups, and the citizens. And so we are really working with our colleagues of the social science, economic part, in order to develop participative approaches in order to have a more effective planning and really get useful results. I show you some examples, and in order to do that, I recall this interesting approach of UNDRR, the 2017. For example, here they proposed a disaster resilience scorecard for cities where you have 10 essentials. Of course, are very small. I would just develop one example, which are a way of address and apply the Sendai framework for disaster risk reduction. Let's just pick the second one. Identify, understand, and use current and future risk scenarios. In this, for example, there are two different levels. One is something applicable in a short time with some questions where the different stakeholder can provide a response in a range from 0 to 3. And then, for example, this is related to the cascading impact. So it's a way of interacting with the stakeholder. And then in this approach, they have another level, the detailed level, where the assessment becomes more careful. There is more time, 1-4 months, and the outcome is more detailed. Just to give you an example of what is going on in the world, which is this approach. In a similar approach, in Italy, we are developing, for example, these two storylines, which are very important. These are photographs taken from different universities of return. You see people sitting around the table with a collaborative approach. We invite also stakeholders and people, representative of associations, really to have this approach where you start with a brief story. So you put a case on the table and you categorize the impact in that sense. You look at the population, public services, critical infrastructure, and natural environment. And then you try to look at the interdependence between these and the cascading impacts. You see all those post-it we put on the screen. And finally, we try to use this tool of impact chain, which is a tool usually adopted for colleagues that study climate change. Now we are adopting this, and this is a very interesting approach because we have a what-if approach. What happens if I do that? And so you can create scenarios, accounting also for the benefit of different strategies, and in this way we can assess cascading impacts and also interdependencies, and the policymakers can use these in order to select the strategies and budget to use. I think I am 15 minutes, and my last slide. In other words, it's very, Professor Ayala asked us very hard questions. Of course, I just gave you my perspective, but I think that earthquake engineering should improve a dialogue with the stakeholder. I wrote multi-stakeholder because a different stakeholder. And it's important really to push towards more resilient communities, because this is, and I think we all agree, a pathway to more inclusive community resilience. Thank you.
Andrea, thank you very much. Thank you very much. Thank you very much. Now we already have the video of Professor Esteva, so please, can you?
Buenas tardes. Muchas gracias por la invitación. Me encantaría recordar por qué vamos a desarrollar la ingeniería sísmica en México, qué la motivó y qué alcanza y qué falta, ¿no? Entonces, miren, cuando yo empecé mi carrera hace bastantes años, yo soy de la generación 53 de la Facultad de Ingeniería. Cuando yo empecé, pues realmente no había ingeniería sísmica, simplemente se usaban coeficientes que la práctica había asignado así sin ninguna base, pero se decía que debería haber una coeficiente sísmico de diseño para que las estructuras fueran aceptadas. Pero ocurrió el temblor del 57, el temblor que derrumbó al Ángel de Independencia, y luego de arriba vino el temblor de 1985, que es el que ha regido un poco las ideas de lo que hay que hacer. A partir de entonces, había muchas cosas sobre que no había la información necesaria. Entonces, yo empecé a trabajar en el área de ingeniería sísmica, pues más bien motivado porque acababa de oír de ocurrir ese temblor del 28 de julio de 1957, que llamamos el temblor del Ángel. Entonces, pues se estableció un grupo que con base en esas experiencias hizo una primera versión de las normas que deberían aplicarse, pero pues eso simplemente no había información suficiente. Bueno, antes de que llegara el temblor de 1965, yo entré a trabajar en el instituto en enero de 1985, o sea, un poco antes del temblor que cambió completamente la historia. Y entonces yo trabajé en dos áreas. Por un lado, en el área experimental, haciendo pruebas de fuerzas laterales contra deformación, pruebas de laboratorio. Y teniendo en cuenta que no nos interesa solamente cuánto aguanta una construcción, sino qué pasa cuando se somete a varios ciclos de carga, ¿sí? Como de un temblor. Y por otro lado, me empecé a trabajar también con el doctor Emilio Rosimbrus, que fue mi mentor, sobre el área de que para qué temblor deberíamos considerar el diseño, teniendo en cuenta que no sabemos cuál es. Entonces eso me motivó a trabajar en el área de establecer criterios de diseño sísmico basados en confiabilidad y en desempeño, o sea, a lo largo del tiempo que conviene hacer en este momento para que a la larga las pérdidas sean menos, sean menos graves y sean la decisión óptima entre lo que va a costar lograr un cierto nivel de seguridad y cuáles son las consecuencias de que no se alcance ese nivel de seguridad. Ese fue el planteamiento, ¿no? Y que es lo que se ha llamado en la ingeniería sísmica como criterios de diseño sísmico basados en desempeño a lo largo del ciclo de vida, básicamente, ¿no? Entonces, eso ha sido lo que yo estudié. Entonces, ello implicó, pues, bueno, primero desarrollar modelos probabilísticos de la ocurrencia de sismos. Sismos que pueden ocurrir en distintas distancias con distintas fuentes, y la suma de todos en un cierto sitio me dice lo que tengo que considerar. O sea, no tengo información, digamos, registrada directamente en el sitio que me interesa, pero sí tengo información de lo que ha ocurrido en sitios cercanos, y entonces eso se logra establecer con lo que se llama las funciones de atenuación de sismos, que quiere decir que son funciones de la magnitud y de la distancia, y de las características del suelo. O sea, esos tres factores influyen. Entonces, todo eso se toma en cuenta para ver qué es lo que me conviene hacer a la hora de establecer criterios de diseño sísmico. Pues muchas gracias por su atención y deseando lo mejor para las actividades de cada uno de ustedes, con el fin de que logremos un fin común, que es el servicio a la sociedad.
Muchas gracias, Luis. Muchas gracias, Luis. De verdad, para aquellos que hemos vivido este instituto, ciertamente este instituto hubiera sido algo muy diferente si Luis no hubiera estado con nosotros. Creo que hay mucho que tenemos que alabar de este gran hombre, que no solamente por su honestidad, por su amistad, por su arraigo a nuestro instituto y a nuestra universidad y a nuestro país, nos ha llevado a los más altos niveles de reconocimiento. Luis, nuevamente muchas gracias y te agradecemos infinitamente hayas hecho el esfuerzo para estar con nosotros, ¿eh? Muchas gracias. Otro aplauso, por favor. Quisiera pedir ahora al doctor Mario Ordaz que nos dé su opinión sobre los temas de esta reunión, este panel. Estoy seguro para todos es conocido el nombre de Mario Ordaz, uno de los más brillantes investigadores y que conlleva mucho de esas lecciones de lo que nos dejó Luis Esteva y con lo que nos dejó Emilio Rosenbluth. Entonces, Mario, le doy la palabra. Muchas gracias. Gracias. I'm sorry, I went to Spanish. No.
Sorry, I'm going to use the time.
That's very good, very good.
Thank you very much, all of you. Thank you, Professor Ayala, for the invitation. I was not sure about the format of this panel, so I thought it was going to be more like a discussion, like a round table or so. So I'm afraid I didn't prepare a presentation. But now, after seeing Professor Esteva's presentation without slides, I don't feel bad. Mine is more or less the same, so I'm following also my mentor. So we have seen in the presentation by Professor Prota that the problem of earthquake disasters, etc., is a very complex problem that should involve the government, the professionals, the people, etc. It's a problem of many different phases, right? But I will talk just about one of these things, of these problems. And this is one of the facets in which I think we have strong challenges, and that there are things that we could do in that respect. And actually, I will take several of the things that Professor Esteva was mentioning. So this intention of studying the earthquake processes, etc., aiming to balance the design decisions between the costs of giving some lateral strength and the cost of the consequences of having accepted that design decision. No, that, as some of you might know, leads to a very interesting concept, which is that we shouldn't be designing for fixed values of return period, or we shouldn't be designing for fixed values of collapse probability, as is more or less the practice in many countries, maybe all countries, with the exception of Mexico and Colombia, I think. Because following this idea of optimum design, we have always tried to find optimum design values, and that leads to different return periods. No? It leads to designing for smaller return periods in high seismicity areas and much longer return periods in low seismicity areas. No? But I think that there are even in that situation, we have very strong challenges there, and which come from the fact that, in my view, the codes, the building codes, the prescriptions that we find in the building codes are do not take into account explicitly the evaluation of the consequences of the design strategy or the design concepts. In other words, we think that if we satisfy certain requirements under a few limit states, then the behavior of the structure will be fine, and we are happy with that. And so we think that the code is implicitly recognizing the necessity of evaluating the consequences, and that they have been evaluated, and the fact that complying with certain requirements tell us that the structure will work fine. But that's not true. No, that's in general, it's not true. Many structures behave badly during earthquakes, and of course the reliability levels that are supposed to be containing codes are essentially fantasy, because they are not really computed for real structures or the structural under design. No? So risk-targeted values are essentially fantasy, because they are computed for generic structures defined by a very few parameters, and not computed for individual structures under design. So this is what I think is the main challenge. How do we do to include in the design process the explicit evaluation of the consequences of the design? In other words, how do we evaluate the losses that will come in the future to the structure itself, to the contents, to the people, and to the downtime? You know, how do we factor in the resilience in the design process? We never check for that. We should be checking for that. Now, why don't we do that now? No, we don't do that now. Why? Well, there are, I think, three main reasons, which I believe are the challenges I would like to put on the table. The three main reasons are that we don't have the right tools to do this analysis, the right computer tools. Second is that we don't have easy ways or accepted ways to evaluate the costs that I was mentioning, the costs of repair, the costs of downtime, loss of people, etc. And also because we don't have good or complete enough descriptions of the future seismic environment. So let me talk a little bit about these three challenges that I see. First one is that we should have, and I think we don't have, tools that allow for analysis and design of structures, automatic design, no, that could allow us to explore the behavior of many different design options, not constrained to the design spectra put into associated to three limit states, but to explore much more design alternatives. No, and tools that could allow us to compute also in an easy way, or at least a reasonably fast way, not only the initial cost of the structure, but also the other costs that I was mentioning, future costs due to the loss action. So this is one tools that allow to do very fast automatic design in order to explore many design options very fast. That's one. The other one is we don't have good methods, I think, or we have primitive methods, I would say, to evaluate the consequences of the design values chosen, or the design alternative chosen. In terms of costs of the future structure during future earthquakes, lives lost, and business interruption or downtime costs. No? So the methods we have now are not really incorporated into the design process. So if you tell a structural design office to compute the cost of the downtime associated to that particular design of the building and a given earthquake scenario, most of the design offices are not ready to do those evaluations. No, so we should train the earthquake engineering profession in order to do that. And the third one is we should have a much better, in order to do a reasonable evaluation of the losses, etc., and the costs of the losses and the consequences of the losses, we should provide the design offices a much better description of the future earthquake environment. So far, the codes provide the design offices with 3 or maybe 2 or 3 design spectra for 2 or 3 limit states. And this is clearly insufficient to do the kind of risk evaluation that I'm trying to describe. So we should provide the engineering profession with a much better description of the future earthquakes that are going to take place. Maybe, as I was discussing in a panel, I think 2 or 3 weeks ago, maybe in the form of a full catalog of earthquakes with the right frequencies of occurrence, with the right amounts of earthquakes that the structure could be expecting during its lifetime. So instead of giving 3 design spectra, we perhaps should give the engineering profession for each project a full catalog of events that are likely to take place in the next 200 years, for instance, or in, let's say, next 200 years. And that would allow to make calculations of losses, downtime losses, evaluate their resilience, etc. And that would help. That would be actually, it would be essential to make this kind of evaluation, which I think should be more or less, in my mind, the shape of the future structural engineering. So the codes should make these calculations mandatory. So not implicitly, but explicitly. So losses should be explicitly calculated. And then perhaps the code could limit some of the risk indicators of this evaluation, perhaps not more than 10 to the -4 lost lives per capita per year, or not more than an average annual loss to the building of 0.1% or something like that, instead of just checking the response limits and believing that if those response limits are satisfied, then the structure is going to behave well. This catalog of earthquakes should include earthquakes or accelegrams that represent earthquakes larger than the design earthquakes, just to see what happens when an earthquake bigger than the life protection limit state looks. And that's it. How to do it in the codes, I don't have it very clear. Perhaps, as I was mentioning, and Professor Esteva knows very well, the code should have just one article, saying you have to design every building in an optimum way, so balancing the initial costs and the costs of future losses. But I don't know. Perhaps, but I think that's a challenge. How to make the designers compute explicitly the consequences of the design decisions.
Thank you, sir. Thank you very much. Thank you very much, Mario. Yes, it was very nice. Thank you. Thank you. I would very much ask to ask our next presenter, that would be Dr. Artur Pinto. Dr. Artur Pinto, former researcher and director of the European Laboratory of Structural Assessment and this Center of Community Research and by the European Union. So it's for me a big pleasure that we have somebody that would give us a perspective of what within the situation of the risk that the world faces in earthquake engineering, the codes could help with that, and what we could actually attain through work from our community, from our groups. Thank you. Artur, very nice. Welcome to Mexico, and we're pleased you're here with us.
Okay, good morning to everybody.
Speak up a little bit.
Thank you, Gustavo. Thank you, Dr. Gustavo Ayala. And it's an honor to be here with you all, but with the person that gave a lot to the earthquake engineering, to this institute, but also to the world, because he is known, Professor Luis Esteva. And before him, you know very well, Emilio Rosenblum also. But Luis is with us, and it's an honor to be here. Gustavo, you are still here, and we'll have your time to have words for you. But thank you for the organization of this event and inviting us to come to Mexico, my city. A little bit troubles with the traffic, but this is normal, is life. Thank you again for the invitation. We hope to give you our ideas, our views on this issue of the resilience or the evolution of the earthquake engineering in the world. I'm not anymore working at the ELSA laboratory, the European Laboratory for Structural Assessment. I retired a few years ago, but I'm still involved in the research, and I visit my colleagues even outside of the laboratory, and I'm trying to be in line or updated with the issues of earthquake engineering and codes, because I have been very involved in the Eurocodes since the beginning of my career, and I'm still involved in that. The question or the challenge that you have put to us is quite demanding. I mean, the future. Sometimes we don't know our future for tomorrow, but the future of earthquake engineering. But you told us also some guidelines. The resilience is your point, and you should be there. We should go a little bit back. I mean, what was the evolution of the earthquake engineer from the past of our colleagues that they came from the safety to the performance-based design, and today we are talking about resilience. There is an evolution. The codes of today that Professor Mario Ordaz was talking about, and questioning them, etc., they had a strong evolution, at least in Europe and in America, they have a strong evolution. There was, the results of the research were somehow included in the codes. We have to refine them and to put them more responding to the societal needs. We are here doing earthquake engineering, doing the codes, etc. For what? To protect lives, to protect the social life also. It's not lives in terms of safety, but to protect or to give the conditions for our society to not be disrupted by some natural hazards. This is the point, and should be the point always. It's clear that in the past, our demands were in terms of safety, life. Afterwards, it was in terms of performance, and performance, we are talking about economics, more or less economics. What we invest, what comes out from the events, okay, and balance that. And nowadays, we are talking about resilience. What is resilience? It's a little bit more than performance. It's, in fact, the capacity of not disturbing the normal life of the society. This is the resilience. I mean, if there is a shock, it comes down, and after we have to recover and to continue with the situation at least as it was before. This is how do we get to this, how much time we need to get to this point, okay? And our colleague Prota, Andrea already told us that this is a complicated, very complicated issue, you see, involving many things, many tools, many technologies even. He has shown a lot of things to us. But we have, if you want to have a response, we have to go to each part, to each one of these elements, and to do what can you do for resilience in the codes, for example. What can we do for how can we increase the resilience with our codes, with our design codes? Now I open parentheses. We are designing, and we have been designing for ductility. Resist an earthquake using ductility. Yes, but ductility has damage if the event occurs. And the point here are what is the level of ductility that we should give to our codes. And for the time being, it seems that we have calibrated this design process, this strength reduction factor in some linear simplified analysis with the economical consequences. I mean, we said we invest, we see what is the estimated costs in case of the events, and we try to balance them. But we are forgetting one thing. If we are talking about resilience, we are forgetting this disruption, the social disruption. And this is, in my opinion, for the codes, the next thing to include. We don't know yet what is the metrics of this resilience, okay? We did it for human life, somehow. We said that one life is 1 GDP per capita. When you do our calculations, we have to be able to do something else, something similar for the case of resilience, recovery. Okay, this is something that I don't know if I have been very structured, but I have put the point on something that could be effective. I mean, in terms of what should you think next for the codes to include this part of social disruption, even in these calibrations. Professor Mario Ordaz went a little bit further because he did more. We don't do the design of our structure with this global simplified methodology. We go structure by structure, and we go there, and we go to the structure, and we try to understand what happens in this and that situation, and earthquakes with these different densities, etc., etc. This is good. It's good the designer to understand what he's doing. What will be the consequences, etc., okay? But this is even a step forward, in my opinion, what I'm talking about. What we should be first is to try to calibrate these simplified methodologies using or including also the social rupture, the rupture of the disruption of the social life, to include it in this balance between the investment and the consequences. This is already a first step that you can do, and it is easy to do, okay? I came to the code, and I suppose that I don't go further on this, but I would like to come back to my 2 or 3 pages of reflection on this. And in fact, I consider here that we have this social part, but we have also ethical and sustainable and global dimensions in this, in the future for the earthquake engineering. Ethical in the sense that what we see here is what we have is we have different consequences of the disasters in developed societies and less developed societies. I mean, is there a problem? Yes, it is a problem. We have to be somehow solidar. We have to apply some kind of solidarity. I mean, we have to get in contact with these less disfavored zones to promote the technology transfer, etc. In zones where we have been developing faster, I mean, we have the responsibility to look at these places where still there is a disaster, there are still deaths, etc. There is an ethical dimension in the earthquake engineer that we can take into consideration. This doesn't mean that we'll be helping or giving money, whatever. This means that we create connections at the level of research, education, etc., with these people, trying to include them to have them to do the transfer, the soft transfer of technology. This is the responsibility also of the earthquake engineer community in the future. And another question is the question of sustainability. In Europe, you have this very in mind, sustainability. I mean, what is the impact in the environment? Earthquake engineer seems to have nothing to do with this. It has to do with this. We are using materials for our structures. We are repairing our structures or demolishing them, and we have to do a balance between we have to include the part of sustainability. You know, we are on a planet, we have to protect our planet. Perhaps it is not the most important component in the protection of the planet, but it has a weight in this protection of the planet. This means that we have the responsibility of thinking about sustainability even in our design. Our codes should have at least one sentence to ask the designer to have in mind these questions of sustainability. Yeah, what I have written here is we have to go along the lines of designing for all. Designing for all means designing for other issues than the safety and performance. For the resilience, yes, we should go this, but we should also design for sustainability and for all in terms of socially, to design also for less favored people in zones, how we can involve them and have them also benefiting from the evolution, from the progress in earthquake engineering in other zones of the country. That is my view of the progress or evolution of the earthquake engineer. There is no need to say that the new technologies will help us in all these things. The AI, the ways, perhaps the colleagues will call about this in the future. Yes, but this is normal. We have done it always. We have always integrated new technologies. Here now, the challenge perhaps is even more, more demanding or is more pressing. But we have always integrated technologies. We have integrated finite element methods when we are doing calculations by hand. But now we have much other things to include, and we have to include them, AI, and other things. Many thanks. I have been already too long. Thank you for your attention. Thank you, Gustavo.
Artur. Thank you very much. Thank you very much for your words and also for all the effort taken to participate and be with us. Thank you very much. Next, I would like to ask Professor Arturo Tena Colunga, a prominent professor of Universidad Autónoma Metropolitana in its unit of Azcapotzalco, that has been recently consolidated like a resilience-oriented man. And I would very much ask him to give those thoughts about the idea of this panel.
Thank you, Professor Ayala, for the invitation. Thank you all. I have a difficult challenge just to try to put my vision in just a few things. This is what I try to explain, but I will go fast about resilience. And since I'm one of those students that changed his love for bridges for earthquake engineering after the 1985 earthquake, basically, I experienced the 1985 earthquake. I didn't like it. That's the reason I studied and specialized on earthquake engineering. And I came to the 2017 earthquake, and I still don't like the results. And I don't like for these kinds of things of the survey. We have like close to 2,500 buildings that were seriously damaged from several parts. I didn't like the quantity taken the size of the earthquake and whatever. I didn't like that most of the damaged structures were for housing, according to the statistics that we had. And if we look at the codes, we have like the 18% were done with collapse prevention, modern codes that they should behave more better given the demands in the places where they were in, that is in the western part of the Lake Texcoco, where the ground motions weren't that intense compared to the design spectra. So basically, if we look at the 1976 code, okay, we could say, okay, that was first, that was surpassed by a far. But if you look 1987, 1995, and 2004, they should have been covered in that region. Then an eternal problem with the structural irregularities. 90% of the damage was on structures with at least one structural irregularity. And it's something that we have to address through research, not through inventions like some are doing. And things that some people don't think, that we have to have a special way to design structures with low redundancy in one direction. They are very vulnerable, as we can see it in here also in the statistics. We didn't decide to build a city when they elect this as an historical decision, but we have this problem with the subsoils, and it's something that we have to take into account, including when we are trying to promote seismic control technologies like, for example, base isolation. That is not a place where we should use base isolation, and some people are saying that they are resilient just because they put it there. And a perennial problem, structural pounding, that is magnified in subsoils. We have to do something about trying to provide better tools to the engineers to get the gaps. This is the statistics of structural pounding is favored by non-synchronicity between the natural periods of the structures. As you can see it, most of them were between +4 - 4 stories where they get this problem. And we, for example, are trying to say that in the subsoils, we have to have at least a gap of 15 centimeters if we want to avoid that the pounding was too strong, or have in the code a equation where the coupling, the synchronization is taken into account to get a more realistic gap. Well, I can do that. Okay, so the seismic design, the traditional collapse prevention, has been good to save lives. That's true. We can check the statistics on the 2070 code, collapse prevention code, less people died. Unfortunately, I have to say that there are some people that died in buildings designed from 1987 to 2017. But the problem, in my opinion, and Professor Pinto said, is that we are favoring to lose life reductions because of ductility. That implies damage. And that's part of the reasons we have these statistics. And this is not only in Mexico, it's in any major earthquake. You see it in New Zealand, you see it in Taiwan. Soon we will see it in the States too. So basically, in Japan, there's not a problem with that. And basically is the problem, I don't think that are the methods. What happened when you reduce with ductility the design spectrum and you take the hysteretic behavior on this one? Well, in subsoils you have a very large reduction factors, and that is very attractive for people, but you are shifting, if you reduce the strength, the period of a very strong, of a very weak structure to travel further and go to resonance in these things. So basically the problem is that we are trying to promote, because many people what understand of dynamic and resonance is an elastic one, that is the graph on the left. But if you go to the nonlinear part, what's happening is that if you reduce with large forces, you are getting the resonance response towards, it's shifting. So some people will say, okay, I have an elastic period of 1.3 seconds and I'm safe because my side period is in 2. No, it is not if you get a large reduction because you are going to have the amplified response there, basically. So what we have to promote in order to do resilience from a part, in my opinion, is that we have to make engineers understand structural dynamics, nonlinear structural dynamics, in order that they don't use on what I call the rocky zone, the yellow one, that is you designing resonance to develop a lot of nonlinear deformations on control, and let's give the tools to engineers to try to move, to shift to the zones of the spectra where you have reduced response that I call the Mayweather zone, doing analogy with boxing. Okay, so we are talking these frameworks of resilience, and what I think is, of course, is complex, and we have to do these things. And you know, the problem is that sometimes this is based on guesses, not on actual data. So basically, is as you see, we have statistics of the earthquakes, and everybody is a paparazzi of what's happening in a recent earthquake, but no one follow up. Well, I follow up. Then, of this inventory of structures I have been following out, and this is just like I could call on soccer. This is my bar video system referee look. I take a place where I know very well that is on the zones where more buildings were damaged. This is an inventory of 28 buildings that either had a partial collapse or collapse, were demolished, or were retargeted. Yeah? That was the way they look on September 2017. That's the way of the recovery thing. And in here, you see that there are some of them that were those lands, some of them that after 7 years, that's where I take this framework where just on a very small part of resilience. So this is not really a good resilience. The recovery of this sector is like 40% 7 years after on housing. Okay, so we have been following those, following up, and I forgot, sorry. So basically, for example, this is an inventory of 237 housing buildings that were demolished or collapsed. And as you see on the blue one, those are the ones that we have not done anything on these buildings. And the ones that have been reconstructed with funds or are in administrative processes, like those that were collapsed and that were demolished almost immediately, some of them, we have not recovered all of them. If we look the way through time, how this had been recovered, well, it doesn't seem that we are doing that great. Basically, from 270, we have just finished a little bit more than 90. And if we want to do resilience and use these integrals and whatever for cost effective, we have to use realistic downtimes and recovering process, because a building that collapsed, the recovery is not like if you start a new building and take the times of a labor work of whatever. And you see here the downtime is the red ones on the circles, and these are the best recoveries in the city. And the green one is the real time where they start to construct, and the dark green is when they finished. And these are the best recoveries within the city that we have realistic data. So it takes more than 7 months. In the average, it took like 14 months from this inventory of buildings, and the downtime is about 15 months. And in these ones, that most of them are from a SLID Foundation, we know that the SLID Foundation has the resources, has the company, has the engineers, has everything. Still, there were some kind of social problems, and still we don't have such fancy times that we recover. Okay, these are 1,041 buildings that need to be retrofitted and that were retargeted or that it means high damage or medium damage. And what we can see here is that we have not recovered most of them. In fact, if we look through time, the recovery, we have recovered about 300 of them until May this year. Okay, so basically is what we have to do, we have to improve resilience, and the way we have to improve resilience is that the new buildings, the codes have to promote buildings that are resilient. Newer buildings, otherwise we were going to have bad inventory. We have to promote that the buildings that are retrofitted are resilient too. Okay, so basically is we don't need fancy methods. We have one of the most resilient buildings in the world, that is Torre Latinoamericana. Both people that were involved in there understand dynamics, understand structural engineering, understand detailing, understand that a good structure doesn't have to be cheap. So that means that it doesn't have cost. This is a favorite from the press. We have resilient retrofits, pioneering exoskeleton retrofits that after it was retrofitted in 1979, nothing happens in 1985, nothing happened in 2017. So basically we can promote in the codes resilient-oriented design with the tools engineers understand. For that, what we have to change is the mindset. We are going to detail the structure so they will have a large ultimate deformation capacity, but we are not going to take all for design. We are just to take, I think this is, okay. We are just going to take this green zone where we have a occupancy or immediate occupancy status, and we, in the Mexican Gulf, we have to have how much of the ductility we are going to reduce and how much of the overstrength we are going to reduce on this one, so we will have this goal of having occupancy and immediate occupancy. Of course, that depends on the system, how much damage you will tolerate. For example, we did this work on masonry, and for example, for confined masonry, of course, this damage is not good, but you can repair that kind of building and still have some ductility and overstrength that can help you to get and achieve that goal. Of course, if you use passive energy dissipation, base isolation, you can do much better, but your goal there is that the structural system for gravitational loading has to remain elastic, and you take all the nonlinear part from the energy dissipation, and then you can still compute which is the ductility that you have and the overstrength that you have for such system that the energy dissipators are going to be replaced on time. I have been working on this. It's not something that it cannot be done. This is about 217 steel buildings where we get the parameters for the Mexican codes and the American codes, for the deformation capacity, for overstrength, how to estimate the natural period, which will be the yielding displacement and the ultimate displacement, depends on the parameters. And you can promote methodologies based on the codes. And for example, this is for reinforced concrete frames, intermediate moment frames with energy dissipators, including solid structure interaction, that we can get a design using, the normal procedures, modal analysis, whatever. You just can get it. You can submit it to a series of records, bidirectional records, where you match the design spectra, or like Mario said, even more. We did it even more for the steel, but I don't have the time. And then you can have your resilience performance. These are the hysteretics. These nice hysteretic loops are from the energy dissipators. The beams, the worst beam is the ones that are marked in here. So they basically remain elastic. No 50% of stiffness loss, as many codes promote damage. in reinforced concrete structures. Then you can see, we design with this envelope. These are the demands, the medium demands, and the peak demands, and these are the residual deformations. You can do it. So basically, on these kind of studies that we have been working with some of my students, we have proposals for the codes of how to, for the Mexican codes, the European code, and the AIC 7, which will be the global design parameter using traditional procedures, and the height limits is with the heights of the buildings that we just studied that were up to 25 studies for. This is for the moment frames, reinforced concrete, and the other ones are for composite moment frames, and I have it for the steel frames. So we need more studies like that for other conventional systems, because not all people likes to use energy dissipation. Some people prefer to use bracing. Some people prefer to use moment frames alone. We can do it. And researchers and their teams should do it, because otherwise we will keep on, having in the codes. I think that if you do this, it will be a better design, and they don't have any study, and they put it in the code, and they force the people to use something that is not a study, and the guys that are designing have to sign responsible of that. I don't think that that is good anymore, because now we have tools, not perfect. Of course, we never will have perfect tools like Mario said, but we have tools to propose better things based on the studies. And in the Romantic times, intuition was very important, because we didn't have that many tools and that many hands. Well, and that will be my vision. Thank you.
Thank you very much, Arturo. Thank you very much. Thank you very much. Yes, thank you.
Thank you.
We move to the next presenter, that would be Khalid Mosalam, professor of Cornell University. Sorry, graduated from Cornell University, professor of UC Berkeley, and for actual director of the PEER. PEER is the Pacific Earthquake Engineering Research Center. And for me, it's a particular honor to welcome Khalid as one of somebody that I admire since he was my student. And we have kept ever since a lovely friendship. And I thank you for making the effort to come into Mexico, and always ready to help us in whatever we ask him for. Khalid, thank you very much.
Thank you. Good afternoon. It's always a pleasure and honor to be here in Mexico City. And thank you for inviting me, and it's a great also opportunity to see Professor Esteva. So we are in Mexico City, a city that perhaps more than any other reminds us why our discipline exists. Every generation, and we heard that from previous speakers, every generation here has witnessed how the earth can challenge both our science and our humanity, and how engineering continues to rise to meet that challenge. As we look toward the future of earthquake engineering, and based on the guidelines from Professor Ayala, I would like to organize my reflections around three simple questions that he posed. What will continue, what will change, and what will be new? First, what will continue? Simply the core ethos of earthquake engineering. This will continue. At its heart, earthquake engineering will always be about protecting life, infrastructure, and communities. The underlying principles of mechanics, materials, and modeling remain the bedrock of our discipline. We may change our tools, but not our purpose. The equations of motion, the constitutive laws, the need to understand energy, stiffness, and ductility, these are timeless. We don't expect any changes there. What will also continue is our commitment to experimentation. Full-scale shaking table tests, hybrid simulation, instrumented field structures will remain essential. They keep us honest. They connect our equations to the real imperfect world. And finally, the spirit of collaboration that defines our field will continue. Through global networks like International Association for Earthquake Engineering, regional leaders like Earthquake Engineering Research Institute, and also Pacific Earthquake Engineering Research Center, which I have the honor to be its director at the moment, and national partners such as Sociedad Mexicana de Ingeniería Sísmica, UNAM Institute de Engineers, that's one of the partners in many of these, National Center for Disaster Prevention here in Mexico. I'm sure I'm missing others. Together, these organizations sustain the open exchange of data, lessons, and innovations that derive resilience that we heard several talks about across borders. And this is very important. That spirit of openness, learning not just from successes, but also from failures, is one of our field's most defining traditions. This will continue. So yes, we will still build models, we will still run experiments, and we will still learn from earthquakes, but we will do all of this faster, smarter, and more interconnected than ever before. And the reasons are obvious. But how? This is what I will touch upon in the second and the third part. So second, what will change? Simply the digitization of our discipline. This will change, whether we like it or not. It doesn't mean our mission will change, but our means will change. We are entering an era where earthquake engineering becomes digital at its core. Until recently, our work was episodic, which means an earthquake strikes, we access the data and assess damage, we update codes, as we heard several talks about that, and then we wait for the next event. But we are now shifting to the so-called continuous learning systems, to a world where infrastructure learns in real time through data, sensing, and computation. I'll speak about the Peer Center a little bit. So at the Peer Center, and also in many other centers around the world, we are building what is called digital twins of bridges, of buildings, of networks. These are living models that mirror real structures, continuously updated with sensor data and things like drone imagery. This digital information means that after an earthquake, we will no longer rely only on slow manual inspection. Instead, autonomous drones, UGVs or unmanned ground vehicles will capture high-resolution imagery, while algorithms trained on thousands or maybe even millions of labeled data sets detect cracks, spalling, and misalignments automatically. the time between shaking and actionable understanding will shrink from weeks and days to hours and perhaps even to minutes. The workflow of our field is changing from linear process. What does that mean? We used to simulate, test, analyze, and report. That's what we used to do. To what we call closed loop, which is to sense, model, predict, and adapt. That's the big shift. AI and the cloud computing are turning earthquake engineering into what is called always-on discipline. This discipline is always turned on. There is no, you don't turn off your computer anymore because everything is running in the cloud. Where every new piece of data refines our models and every event contributes to a shared global learning ecosystem. So the change is not that we analyze better. We have been doing that for many years. It is that we analyze continuously. And that continuity is the shift in the future. Third, what will be new? And again, in short answer, AI, autonomy, and integrated intelligence. What will be new are the technologies and methodologies reshaping that ecosystem. Again, whether we like it or not, it will happen. The most transformative force is artificial intelligence. Not as a buzzword, but as a scientific instrument. In the coming decade, AI will be embedded at every stage of the earthquake engineering pipeline. And I will list the three things here. Computer vision. Computer vision systems now recognize cracks, drift patterns, and concrete distress as reliably as trained inspectors. And they can do so at a scale from the air or from the ground, using drones or ground vehicle. Natural language processing, which we all use when we run a ChatGPT to check the language of your email or something like that. These can already parse inspection logs, research papers, and damage reports to automatically summarize lessons learned across decades of data. If you look, we have in PEER, we are reaching report number 1,000. We have about 500 plus ERC report. We have about close to 400 plus peer reports. If you add up just the knowledge in these reports and set it up vertically, probably it will be about 3-story high. We can take all this knowledge and using NLP and summarize it. Will take us decades for an army of people to learn what's in these documents. But now, with the summarization tools, we can capture this knowledge much faster. So this is something we cannot hide from. Bayesian learning and hybrid AI mechanics models are being used to update analytical models on the fly, adjusting stiffness and damping estimates as new sensor data streams in. Meanwhile, autonomous systems, drones, UGVs, and sensor-equipped robots will become our field assistants. They will fly into damaged areas, crawl under bridges, and map 3D environments in real time. They will not replace field engineers, but they will make our assessment faster, safer, and more complete. And beyond AI, we are beginning to see what is called generative and predictive models. These are networks like temporal convolutional networks and transformers, which are used in things like ChatGPT, that can learn the statistical patterns of ground motion and the structural response. They can forecast likely damage states, generate synthetic scenarios for design, or guide where to allocate inspection resources first. So the new paradigm in this, in my opinion, is that AI will not replace engineer, it will amplify the engineer's capacity. It will allow us to do in hours and minutes what once took weeks and maybe longer, and to simulate thousands of scenarios before a single earthquake strikes. So these are the answers of the 3 questions, but I have a few other things I would like to stress that some of it were mentioned. There is a human and societal dimension in all this, and we shouldn't forget that. Amid all this technology, we must never lose sight of the human mission of our discipline. Earthquake engineering is not just about structural and geotechnical systems. It is about people, about dignity, and about equity. We must ensure that this new wave of digital tools not deepen inequality. And it was mentioned before that it benefits not only wealthy cities with a smart infrastructure, but also developing regions where seismic vulnerability remains highest. I mean, a magnitude 6 earthquake in Japan probably will do nothing. A magnitude 6 earthquake in Cairo will kill thousands, if not millions of people, because just this city is not as prepared. So we have to make sure these solutions are seen by this large mass of people in these vulnerable places. Digital resilience must be inclusive resilience. Another key challenge and opportunity lies in education. I am an educator, I teach classes. The next generation of earthquake engineers must be bilingual. I don't mean English and Spanish, which it will be wonderful to speak English and Spanish. They have to be fluent in physics and in data science. They should understand both finite elements and neural networks, both constitutive models and convolutional models, and they must be taught to use AI critically and responsibly as a tool for insight, not automation, not to solve your homework quickly. Right? Finally, we must remember that some parts of our work can never be digitized. The empathy to support communities after disasters, the judgment of weighing uncertainty, and here in this table we have an expert in uncertainty. That's irreplaceable, is what are the sources of uncertainty? This cannot be digitized. And the ethical responsibility to put public safety above all else. Data and AI may give us speed and precision, but wisdom will always come from the human mind. Looking ahead, and I have to close saying what actually PEER will do, the PEER vision and global agenda, as we look ahead, institutions like PEER are evolving from research consortia into digital innovation hubs for seismic resilience. Our current efforts focus on integrating 3 pillars: sensing from drones, cameras, and structural health monitoring systems, modeling through digital twins and that merge physics and data, and decision support, which is powered by AI and probabilistic inference. Some of these are not new. These are not abstract ideas. They are being implemented right now through innovations like BRACE2, which stands for Bridge Rapid Assessment Center for Extreme Events. We are creating digital twins for over 80 bridges across California, updating their condition through fusion of data and environmental conditions. We are linking these models to real-time earthquake simulations, including physics-based regional scale simulated ground motion through peer LBNL SGMD. SGMD stands for Simulated Ground Motion Database. This is analogous to what peer had long time ago, the NGA. NGA was for recorded motion. SGMD is for physics-based simulated ground motion. We're starting with the entire Bay Area, we're moving to SoCal, we're moving to New Madrid Fault. This is modeling everything we know of the geology, of the soil conditions, using wave propagation, physics, supercomputing to generate data at a grid of 6 meters apart. So this will be trillions of ground motion signals that will be at our hands. And we cannot make use of it without AI technology. We are linking these models to real-time earthquake simulation, as I mentioned, and rapid damage forecasting, bridging the gap between data, mechanics, and decision-making. At the same time, our collaborations with Caltrans, FEMA, and international partners are extending peers' methods into transportation network, energy infrastructure, and urban systems. This is how the field will evolve, in my opinion, from designing for safety to designing for resilience, adaptability, and recovery, from responding to disasters to anticipating and learning from them continuously. And at the global scale, we must ensure interoperability, that our digital twins, our data schemas, and our AI models speak a common language so that knowledge from one region benefits all. So at closing my reflections, what will continue? Our purpose to protect lives and communities. What will change? Our tools, from equations and blueprints to sensors and digital twins. And what will be new? Our capabilities to sense, learn, and decide in real time. But beneath all these transformations lies a simple truth. Our mission is no longer just to prevent collapse. It is to ensure rapid recovery, adaptive learning, and lasting resilience. The tools have changed from drafting tables to drones, from hand plots to hybrid models, but the purpose remains the same: to transform uncertainty into preparedness and data into resilience. Thank you.
Thank you very much, Khalid. It was very nice to hear you. All right, thank you very much. Our next presenter would be Professor Lars Abrahamczyk. That he comes from the University of Weimar in Germany, and he is responsible of some activities very much for the understanding of that data information that we need to actually achieve resilience. So we would very much like to hear your opinion about what we're talking about in this minute.
Thank you very much, Gustavo. Also, thank you very much for inviting me to this session. I guess I'm the youngest one, yeah. So for me, it's probably the most.
No, we are.
Okay, yeah. Then might be the less experienced one. Yeah.
We are.
Yeah, and from that point of view, it's a great pleasure for me to contribute to this discussion, and I can just say also following what has been said so far, but I would thought about what I can contribute to it, and I decided to have a first look a little bit into the past, because understanding from where we come might gives us also a chance to talk about the future. And looking to the past, so earthquake engineering is actually nothing new. So and earthquakes has caused casualties, damage since centuries, and also measuring earthquakes has been for a long time a challenge, but it's also nothing new. So, and from that point of view, there was a great development in the last 50 years, I would say. Yeah, when you look at this slide, so there was a first instrument by a Chinese mathematician. Nowadays, every smartphone has a small sensor in it, which we can use as a seismometer as well. So there's a huge development, and we gather much more data nowadays. But if you look also a little bit to the back, so we just starting measuring earthquakes as we do and use it since now. Just 70, 100 years almost. Yeah, so the first earthquake record or first strong motion has been set in the 1930s. Yeah, that means our knowledge about the earthquakes and this particular size has changed tremendously in the last couple of centuries. And there's also a nice plot how much sensors has been used in the past from this kind of development. And nowadays we have really a nice picture about what happens, and where we get also ideas about the strongness of the earthquakes and what's the actually frequency content and so on. So that means there was a huge gain of knowledge in the past centuries. And I think that's something which we can acknowledge a lot, and which we have to address also in our future development and where we will go, because we get this. But on the other hand, so what we are always doing, we are learning from the observations, and I think that has been stressed out already, so that we always see the consequences and that we want to act on the consequences. We want, in the future, we don't want to react, we want to prevent, but all the observations gives us the ideas how to deal with it as engineers. We develop models based on that we can prevent these kind of things. So I think this is quite common among our community. But it also leads us to different frameworks, how we can deal with this topic, particularly in the direction of communities. What are the consequences of earthquakes? So how can we prepare, how we can increase preparedness, and therefore we have this kind of frameworks. We have different tools. Some are more empirical, others are more analytical, but at the final end we can already do that, so we can come up with some prognosis, we can come up with studies, and that's actually what Mosalam also mentioned, that actually the tools are in our hand and we might get much faster. But here I could also already say the challenge will be how to communicate these results to the decision makers, that we really come into consequences, that there something changes. Also there was a talk, how long does it take to react, so to improve our buildings again, so to this downtime, to minimize that. So that's, I think, one of the key challenges in the future is how to communicate our results and to the decision makers, to include the communities, that we avoid this amount of damage. And this is a study here for Antakya. You might have heard about this tremendous earthquake in the southern tip of Turkey, so where there was a huge loss of life and value. And there we did a study in the past, so which we could actually anticipated the amount, but to get into action is really a challenge. And here I just would underline all my previous speakers who talked about that we have to do this community, to bring them into it, to get into better resilience. We have also the tools about distinguishing daytime, nighttime, what are the probable casualties, so this is all what has driven us to develop, We have this very nice tools in hand, so with talking about what is the collapse, or how to simulate things, we already addressed in some slides, so that we want to shift to discuss the probable damage and the limit states. I think I have it in the last slide as well, because that's also something about communication. And I think communication will be definitely one of our next issues, how to communicate what will be the acceptable probable damage in our design procedures. and this needs to be addressed. And that's also the key challenge for us. So if we are at universities, we have to train the next generation of engineers in this direction, that this is very open communicated into this society. But this leads also to some problems which we still face. And here I have a plot from a blind test, which are quite often done. Probably Mosalam can report about that as well. And I think that's a very great thing to do this more often, because it shows us what are our limits so far. Yeah, so we are very good at the prediction of the response in the linear range, but if it goes really into the nonlinear range and in the damage, then we might face quite often some problems. And what you can see here is actually the perfect world would be all our points are in the diagonal line in the center from it, but we are far beyond that. So that shows actually that our predictions are still not as good as it could be. And here I can just continue the future possibilities with all the new upcoming tools, AI, large language models and so on, that we much get closer to that. Also, this digital twin will help us, but the digital twin, from my point of view, they first gives us the idea about the current state and not what will happen in case of a nonlinear or nonlinear situation. But nevertheless, it will improve our knowledge in this direction a lot. Yeah. So here also another figure about that, about the fundamental period. So where we already faced by some, where we would say rather simple parameters. Yeah, we are still not very certain about that, and there we have to improve a lot. And there I see also the challenges for our doing, or the directions where we still have to go. On the other hand, also to stress out a little bit these limit states discussions, I would say from the previous damage pictures, we could see there were some collapse and so on. On the other hand, our codes already get in place and improve the situation. And there are some pictures from the Albania earthquake where we did a reconnaissance mission, and where we could see that the structural system performed pretty well. Yeah, so that means our codes worked out what we promised, more or less. Yeah, but what we hadn't under that good control, particularly in that case, from my perspective, was the non-structural elements. So that means actually we definitely will see a shift in the limit states and the acceptance of damages, which will drive our future direction in earthquake engineering, and particular also in the communication of what might happen to get to a resilient society, community, as Dr. Ayala wants to discuss and to go. Yeah, here's some images from the infill walls damage, also the interior damages, which were tremendous, which leads to a huge downtime or a huge loss, whereas the structural system remained more or less undamaged. Yeah. On the other hand, we have these nice tools, which we also were mentioned by my previous speakers. Yeah, we have everything in hand. We need now students who can deal with that, so we have to be good teachers in this direction, to train students to understand this. Yeah, and this is my real opinion. It doesn't help to use ChatGPT and so on. It can be a tool, but we need really to understand the physics and the methods behind. And this also not only the young engineers, but also the practitioners, because only then we get into a resilient community. Yeah, so what we did in the past, we tried to do this also for historical structures. Yeah, so we have nowadays these tools, whereas there are a lot of uncertainties in it. But I think the capabilities are there. We just need to do it and to train it for the further directions. And this brings me actually already to the challenges and opportunities. So I tried to keep it very brief. Yeah, and the challenges which I see and I hope to address already a bit is we still need more validation. Yeah, we need to validate our models. We have to still further improve our models, and this is where research really has to contribute to that. And thanks to all the facilities that we have, the shake table tests, and nowadays the much more computational power, I see this as a challenge, but also as a challenge that can be reached rather fast. A challenge will be definitely the definition and acceptance of limit states, because that's nothing which we can do alone as structural engineers. This is a society issue, and there we need communication. And for us as engineers who are sometimes not that communicative, I think that's definitely also a challenge for us, how to communicate this and to get linked. But that's actually very appreciated, the discussions previously. We need these community models where we get introduced by all disciplines into the discussion. On the other hand, I see also a challenge to develop simplified models. And simplified methods, because what I have shown, we have this huge numerical models, we have the computational power, but on the other hand, I think simplified methods, rules of thumbs, gives us the certainty that we go in the right direction, and we have to make things more simple, because if we can't describe it in a simple way, then we can better communicate it. And the last challenge, which I also see from the events that we had in the near or recent past, so for example, this event in Turkey, we have cascading events, we have multi-hazard events, which we haven't addressed so far or that much in our studies, also not in our standards, and that's also a challenge and opportunity for the upcoming, I wouldn't say centuries, but for the upcoming years. And from the opportunities point of view, I think it has been stressed out already a lot. So the computational power, the large language models and all these kind of things, the access to data, so the principal access, so how to deal with this amount of data, that's another issue, but therefore we have also the computational tools nowadays. I think this gives us really opportunities to evolve very fast and in a very good direction. And the other opportunities, and that's very acknowledged to you, Gustavo, is actually the cooperation possibilities, because this gives us also more power to develop these things all together, because it's not, as Mosalam also already mentioned, it's nothing stopped at the border. The earthquake waves doesn't stop at the border, and that's a cooperation problem. And we have to collaborate, and nowadays I think that got much easier than centuries ago. Thank you very much.
Thank you very much, Lars. Thank you very much. It was a very nice presentation. Thank you very much. All right. Well, we should continue now, and I will ask Professor José Manuel Jara Guerrero, professor at the Universidad Michoacana, San Nicolás Hidalgo, in the beautiful city of Morelia, former student of this university and a prominent researcher in many aspects of risk analysis and earthquake engineering. José Manuel, welcome again, and nice to hear your thoughts about these topics. Thank you.
Thank you. And first of all, thank you, Professor Ayala, for inviting me. And I have to start saying that it's a really honor for me to be here in this table with the Professor Luis Esteva. Well, what I prepare is related to see where we are moving to, and obviously with the theme of the seismic engineering and the resilience. Seismic actions have been included for designing a structure since the last century. For example, in the 90s only for gravity loads, then in the 20s there were used a uniform seismic coefficient. In the 40s, start to work with the dynamic characteristic of the structures. Close to the 70s, it was the proposals for a period-dependent forces and elastic analysis. And after the 70s, it started to see what we call the modern regulation codes, but it's starting to use the term of ductility and appears the force-based design and the modification factors, reduction factors in some other codes, and design spectra. So after that, in the 19s, we start talking about the importance of displacement demands for assessing damages, the relation between these two parameters, the displacement by design. It was a very important document, the ATC 40, that introduced the nonlinear static analysis and the capacity of the buildings to define the demands. And after that, in this century appeared the performance-based design. One very important document, the Vision 2000, that established a matrix of performance, the document FEMA P58, and we started to use the incremental dynamic analysis at talking about seismic resilience. So, but what we were expecting were the force-based design way. Well, when frequent earthquakes occur, no damage. We design earthquakes, reparable damage in a very simple way, and with infrequent earthquakes, the collapse prevention. But what we see every day after we have a strong earthquake in the world? Well, even the main goal of this methodology is to protect human lives that many speakers before me have already mentioned, by preventing the collapse of the structures. It's also considered in what is called the equal displacement rule. That is one way, very simple to get the displacement demand of the structures, but it's also, unfortunately, one of the best, of the main weakness. So when we see this picture and after an earthquake, we see these pictures, we immediately think something in us, something is not working well with this philosophy, among other things. If we look just one statistic, it's supposed that this methodology is trying to protect human losses. When we see a statistic like this one, the USGS is, we have considered the human losses of different strong earthquakes. And if we just take a look at the earthquakes of this century in this graph, well, we found really, really large human losses, so obviously economic as well. But we see that even it is a multifactorial, the reason that it happens is something that we cannot accept today. So the force-based design, particularly, I'm going to show what is happening in semi parts of the world after a disaster occurs because of the earthquake's occurrence, and it's no exception in Mexico. In Mexico City, for example, in the soft soil zone, we have used seismic coefficient, what is the highest amplitude of the response spectrum. And these are the values for different codes in Mexico City since 1957. So it changed to 66 to values similar to this in 76, in 2004, and in 2023, we have values close to this value. But we have to accept that when we just increasing, obviously they are not the only changes in the regulation code. There are other changes that have shown that the result could be better when the earthquake occurs. But we have to accept that in general, just this methodology of force-based design, just increasing the seismic coefficient, it's obviously produce less damage in frequent earthquakes, but it's not necessarily the same for design on or infrequent earthquakes. So the document that I mentioned before, this is the matrix that for the first time is a relationship established between the performance level and earthquake design levels. And so in the diagonal, we have the main objectives, the basic objective, for example, for housing or for short bridges, short span bridges. When we have frequent earthquake, we're supposed to have fully operational performance, and with a very rare earthquake, we would waiting for a behavior performance level near collapse. So in the next diagonal, that it includes hospital, for example, or bridges in a urban area like Mexico City. So in this essential objective, we just accept for the very rare design level, life safety, or even the more important structure for society, we will only accept operational performance after a very rare earthquake. So it goes naturally to the performance-based design, where it is not the only main objective is to prevent collapse. So immediately after this, we have started working a little more papers published with the loss models, when we try to evaluate what is called the engineering demand parameters, and with this information, fragility curves, and finally evaluate the expected losses of these events. I have to mention that in the last 25 years, we have been published several papers related with these topics, but I also have to say that there were important contributions of Professor Luis Esteva beginning in the late 60s, when he was talking of economical aspects, the economical failures after the earthquakes, and subsequent studies of the Professor Esteva. He was working the life cycle of a structure, now very close related with resilience. So just to remember the seismic risk, that is a consequence of having the opportunity of evaluating the economic losses. So we have three systems that the intersection of them can define the seismic risks: the seismic hazard, seismic vulnerability, and exposure. The seismic vulnerability, by the way, is we have to accept as well that unfortunately, in the world that we live, the lower income population suffer excessively greater losses. It's a fact, and it also happened that the higher income countries, even living in sites with risk, have greater capacity to mitigate and recover from the effects of earthquakes. So factors that increase vulnerability include that is important in countries like Mexico, particularly the cities out of Mexico City, that the lack of hazard perception among individuals and officials in governments produce a lack of preparedness. So local government that should be responsible for keeping the seismic regulation codes up to date and enforcing their use, not always they are working well with this issue. So earthquake effects normally cause, we have casualties, the structural damages, and we almost focus it in most of the time, most of the paper published in focus on human and economic losses. Less attention we have paid to community impacts that we are talking now in this panel about services, sanitation, healthcare, education, public transportation, among others. And of course, there are, nowadays it's improving the number of papers that are working with this area, but less attention also to non-structural damages. So naturally, we get with the one parameter quite relevant for evaluating resilience, yes, that is the loss of functionality. So damage to infrastructure can give rise, we have to recognize as well, that's particularly in subtype of infrastructure, other hazards, like the one I mentioned in this slide hazardous materials, for example, the release of these materials, but can also have a multi-scale impacts that we usually not consider, and that we start working in several papers in the world about this topic. But we have to consider that this multiple scale impact include the physical and emotional trauma for the people, displacement of families, disruption of community services, loss of functionality, of course, of bridges, buildings, lifeline systems. And that, considering all of this, a multidisciplinary approach should be considered social, economic, and technical aspects if we want to evaluate resilience. So I'm going to pass very fast this one, but I think that all of the previous speakers were talking about this. Just remember that the community resilience include, obviously, as a very important part, the social unit, but we see definition like the one I show in here, these two definitions. We have to accept that resilience is completely related with human component. We cannot separate these parameters. So in general terms, all of us now, we recognize that all the impacts of earthquakes are related with functionality, the downtime that it was previously talking here in a previous presentation, that all of them have a direct effect on people, and all of them are totally connected. So there is just an example to what we have mentioned before about the cascade effects, and there is just a cascade effect related with the earthquake in New Zealand in 2011, that the city central business district in this part, 90% of the close to 2,000 buildings were in safe condition. So the city decided to impose a cordon around this part. So what we see as a cascade effect, just talking about buildings in this case, is that this cordon was involved all the part that the city considered that it was in unsafe condition, but there were inside this cordon many buildings that only had minor damages. So the cordon was for all of them. So we have also loss of functionality when you have accessibility compromise, like in the case in this part of New Zealand. So what is something that I want to point out, particularly for bridge resilience, because even though we are talking more about buildings, bridges have their particular aspect that we have to consider as multi-hazard analysis. Every transportation system should include bridges, and bridges are usually, we have to conduct analysis, multi-hazard analysis, because bridges are subjected to earthquake, scour, corrosion, thermal cycle, and the state of transportation is normally crucial to evaluate effect an earthquake. And nowadays, most of the studies, however, have been conducted on small groups of bridges or special bridges. It was also in some other studies determining the combination of hazard vulnerability and the bridge importance, and or some other studies studying the post-disaster network impact after an earthquake, but evaluated just considering the traffic flow before and after the earthquake. Something that is missing is to relate this network and the effects of the damage in the system with the lifeline system as well. And engineering demand parameters that I mentioned before have focused on relate these elements with fragility analysis and damage limited states. I think that we have to take the next step to link the engineering demand parameters with loss of functionality. I'm not to talk more about this, that it was previously mentioned. Just the bottom of the slide, that we have to consider that one difference between buildings and bridges, that's that usually in bridges is very often that we consider the possible in the service life of the bridges to have a maintenance activity. So any resilient study related with which it should be considered this parameter. So I think in the future, particularly for places like Mexico, I think we have to improve, and I'm talking about many cities in Mexico. It's not probably the case of Mexico City, no, I'm not sure, but maybe it's different. But we have to improve the communication among university owners, governmental officials, and of course the policy makers. To enhance communication with the communities in areas at risk of disasters, keep regulation codes up to date, and enforcing their use, include social units in the seismic risk assessment. It's something that I think is really important when we are talking about community resilience. And to expand the research to assess the loss of functionality in urban areas after disasters, promote research on transportation resilience, including social, economic, and technical aspects. In the technical part, particularly for bridges, and it is related that it was mentioned in a previous presentation as well, I think that we should increase the use of smart sensors in bridges for deliver real-time data. This is quite important, and in the last decades, the cost of sensors have been dropping, so it's a possibility that is actually working in many countries, not in generally way in Mexico. But we have to improve the digital twin models, as it was mentioned before, because in this way we can update with data from its physical instrumented twin. We can have the digital model and the instrumented bridge, so we can prevent some of the damage that we usually have. If we have a link between AI and digital twins, we can have have better information about the structural health, load-bearing capacity. We can even predict deterioration, and the timely maintenance is very important for bridges. And of course, the use of passive and semi-active control, as it is fundamental to improve the behavior of the bridges and buildings in the future. And it will link the AI with visual inspection, particularly in bridges, because it's a very frequent activity to make visual inspection in bridges, combining with those aspects of information, we finally could have more reliable information. And of course, that activity that was mentioned by Professor Mario Ordaz, I think that some work had been conducted to create automatic models, like this one called in the building information modeling, that they are virtual models, and what is the most important part, that creating these virtual models is possible to make simulation, to change anything in a model, and to see the effect of the change of this model in the possible behavior in the future. So what is missing probably is the connection between building information model to create interfaces with the program that traditionally we are using, the software that we are using to evaluate structures. If we can integrate this model with digital twin, it could be a much better information. And all of this can give us the opportunity to make a long-term performance evaluation. So this is, for example, one bridge digital twins in one of example of the studies or the creation of building information modeling of a real bridge. Thank you very much.
Thank you very much, Mr. Manuel. Thank you very much. Our last presenter is, we couldn't miss the chance, and we twist his arm to come to Mexico, despite his busy schedule. And we ask Professor Guido Camata, professor of University di Asunción, Chieti Pescara,
yes,
in Italy, and to tell us something that perhaps it was not very much touching here. That is the fact that you've been involved and giving to the practitioners of earthquake engineering those pieces of information that are required to actually do the right thing as the aims of earthquake engineering by having simpler models that are understood and used properly, and also for providing them the tools for monitoring the structure. So that experience, how you face it as far as what should be the future of these things. Guido, welcome to Mexico. And I think, by the way, he just arrived at 8 o'clock this morning, all the way from Istanbul. All right. So
thank you very much. Thank you very much, Gustavo.
You. Welcome.
It's great to be here. Great to be in this institution because I know very famous people come from here, like Professor Esteva, Rosenbluth. We were talking when you came last time. So it's very exciting. I'm honored to be here because you are definitely one of the most important, for sure, university for earthquake engineering. Plus, Mexico City is one of my favorite cities, so I'm very happy. I'm going to spend the weekend here. My wife is joining, so I'm even happier. So I'm very happy to be here. So my presentation today is more narrower compared to the presentation we had before, but I'm very happy because I thought I'm going to talk about something that nobody cares about or something that is not interesting. In reality, it was introduced by all of you, so by everybody. So now I'm going to be deeper, I'm going to go deeper in certain aspects that we dealt today with. So first of all, I think Professor Ordaz talked about uncertainties in the input of the spectra. Is perfectly right. It's something that one of the most unknown, for sure, parameters we have. This is a recent earthquake in Amatrice in Italy. You can see the design spectrum, and you can see the actual spectrum that is more than the double of the design spectrum. So basically, the expected earthquake is double. The actual earthquake is double than the design earthquake. And that comes the other aspect. If there is such a huge earthquake, it's very important to have ductile systems, so to have plasticity, to have systems that can dissipate this energy. Otherwise, it's impossible to withstand this type of earthquakes. So ductility is one of the most important things that we need to consider. But to consider ductility, to consider real behavior of these structures, we need to move forward. We can't base our design into simple elastic design with Q factors, reduction factors that are very simplified, that cannot represent what is the ultimate limit state of the earthquakes. So it's very important, and everybody talked today about it, to develop new tools and to be able to use the new tools, because something we didn't consider today is the fact, there are tools now available, but we don't have practitioners or even researchers often able to use these tools. So very advanced, we will see numerical analysis, artificial intelligence, sensors, and digital twins is exactly my talk today, so I'm very happy because everybody talk about it. So because exactly what we do is we develop advanced models and we implement it so far in OpenSea, is actually in open source for free, so everybody can use it. And we use also OpenSea for digital twinning, so it's very important to know that it's also in open source, everything is easy to use. So we started talking today about different type of modeling for structures. So starting from very simple model, like lump plasticity, we can use lump plasticity decouple, or even now there are more advanced models that can also consider the axial flexural interaction or even axial shear interaction in two ways. There are more advanced models like distributed plasticity, even with like fiber sections, or even into more complex models like 2D models or 3D models, in which we need to consider even the biaxial or triaxial component of the concrete, and we can consider, we will see bond slip, buckling of the rebars, and in a very advanced way, okay? And lump plasticity is very simple, can definitely model very large models, can be used for regional even approaches, but they have a lot of like drawbacks. cannot describe very well a lot of mechanisms, and it's very simplified. Now we have tools, and we have also the computer power to instead have better description of what is the behavior of the structures. And it's very important, I think, to train the people to use them, because we keep on basically using old tools when now available. We have very modern tools that can be used. But as I said, needed to be validated, but especially people need to be trained to use them. And that's very important because, as I said, it's the biggest uncertainty that we have. If you take one analyst and another analyst, they get two different results. Doesn't mean that that tool doesn't work. It means that people are not trained to use them. And this actually, I go back 1 second. This is actually a model from Professor Mosalam, but I don't know why it's not working the video. Anyway, it's a typical fiber element in which you see the description of fiber section with distributed plasticity, and you can even model the infills and with also the removal of the infills when the infills goes out of plane and basically fails. But then these are the models more I'm interested in. Can we use these tools, advanced tools, to model like large buildings? This is a new future. This, I think, is what is the future of earthquake engineering, also to use this type of tools, also from practitioners. What are now the problems we have? As I said, knowledge. A lot of also engineers are skeptical about these tools, and I understand because they are very complex to understand. So that's the reason, because we need larger validations to use these tools. But as you can see, we can model buildings with considering the triaxial behavior of the concrete, so considering the confinement that is very important, especially in earthquake engineering, considering the bond slip of the rebars, consider the buckling. Everything is possible, and if you look at the shear walls, I showed the video, the shear walls there is modeled, this is an experimental result, and is modeled, each rebar is modeled, considering, as I said, the buckling of the rebars, but as you can see, you can even consider fracture of the concrete. So you can go into highly nonlinear behavior. How can we do that? Not anymore relying on implicit solutions. We normally mix explicit with implicit solutions, and typically we go at the material level in explicit solution, and then we basically correct the result with the implicit solution at the global level. This allows us to have 2 iterations, typically, instead of 50, 60 iterations. So this means that a model like that in cyclics can run in 7, 8 minutes instead of 2, 3 hours. And this is the future, I think, of computation. We need to improve these tools to be able to use them for large models, not for small models. And so just to give you an idea, this actually is a model that we developed for UCSD, San Diego, Professor Conte. This is a very complex model because it starts failing in fracture and then it fails in shear. It's called the Mastianek wall. It runs in 1 minute, okay, the entire cyclic. So it means that it's possible to even do models like that can also be effective. If you can see, like at a certain point, the model diverged from the experimental result is because we weren't modeling the buckling of the rebars. So we know obviously the limitation sometimes, but if we include also the buckling, we can also model beyond this, like this level. And as you can see, you can model very sophisticated models, as I said, considering, for example, punching shear. That is one of the most complex analysis that you can make in cycling, especially. And you can see that the numerical pattern compared to the experimental pattern can be modeled very in large detail. And you can also use some modeling for this type of buildings. So think about it, you can model a certain part of the building with a very detailed model, and then use more simplified models for to model the larger building. So you can consider the correct boundary conditions, but you can consider the detailed behavior of the building. And this OpenSys is perfect for that because you can basically use 1D element, 2D element, 3D elements in the same model, and all in the nonlinear, basically, with their nonlinear behavior. So you can model large buildings, large bridges, considering basically different type of elements and optimizing your model. The videos, they don't work all of them, but anyway, it's not important. Yeah, now it's working. So you can see basically the failure, how it propagates. And this actually is a part of an entire building, but I am showing only the detail. And on the left, just to give you an idea, is without shear links, on the right with shear links, and you can even see the different failure patterns. On the left is less ductile, and the right is more ductile. So you can model even this type of failure. Or this morning I was talking to a researcher who told me like that part of his research is frame infill interaction. Also this, we have a lot of simplified model with strat models that cannot consider a lot of issues, for example, the increased shear forces on the frames. And now you can model, definitely with these improved models, you can model the infill, even using the singular brick, separated brick, and model it with interaction, for example, contacts element that consider also this in explicit solution, so they can also be very stable. And or masonry walls, you can model them with homogeneous material, but even using orthotropy. So in this case, we model, for example, the mortar and the brick separately, and you can model also large building using these approaches. That's very important with the mortar because typically we use homogeneous materials, isotropic, but masonry is orthotropic, and it's very important to consider orthotropy, to consider failure modes. Or out-of-plane failure like this one, that as a typical shear behavior, and is always, you can see it fails in shear, not in flexure, because the brick is actually, the deformation is very important, the shear deformation of the brick, and also in this case, we can model this type of structure. But often they tell me, yeah, but you can't model like entire buildings like that. So this is an entire building model brick by brick, and this entire building model in cyclic behavior using this type of approaches. And these are results comparing this test made in Neo Center, and this is a test compared with experimental and numerical. So there is validation around. You just need to train, as I said, the people and to validate these models. Another thing that I wanted to show you, also another model with masonry, and to show the performance of this type of models, but I think also in this case it's not working the video because I need to push the video, but can you push on the video? Is there, you can go on and if you go on the slide, no, okay, you can, it's fine. Oh, no, it's fine. Anyway, like, it's fine, no, don't worry. I just show directly the results.
No, I think it will show you over here on the screen over there, on the back. I'm sorry.
What do you mean? Oh, it was showing? But it's not working anymore now, the slide. Can you go back to the slide? I think you need to click on the slide. Yeah, click there, so you can see. It's not working anyway. Okay, let's go to the next one. Let's go to the next one. So you can see the results now, the red and the black, comparison between experimental and numerical results. And I couldn't show you from the video, but this was a problem of pounding. So the two buildings were going in pounding. And that's a very complex behavior to consider because it's high frequency, okay? So typically in implicit solution, you have no convergence because the frequency is too high. And you can see how stable is the behavior. So you can model easily also pounding for this type of structures, also high frequency components. So as you can see the results in terms of displacement, acceleration is good. So we can definitely go into this type of analysis. Another thing that today was mentioned is soil structure interaction, especially starting from the faults. Also there are some videos. This is actually a model made by a Chilean professor, Professor Abel, that implemented the OpenSea's the domain reduction method. And in this way, you can model even starting from the faults directly to basically the soil interaction model. This instead is a model also of soil structure interaction. As you can see, we can model directly the entire mountain and see the amplification and the reflection of the waves, as you can see. And going to also in this case was an example of impact of pounding between the structures. This is a structure of the 15th century, but it's not working the video, but it's fine anyway. Oh, let's go to the next one. I think it's stopped. Okay, this damage. I go to the next one. Another topic that was discussed today, how we can improve these models and how can we make basically these models that are more real, okay? So they are called digital twin. So typically, the best way to do it is to use sensors. So you place sensors on the structure. Several types of sensors could be accelerometers, inclinometers, gyroscopes, crack meters, potentiometers. So you can measure basically a lot of different measurements. So you can basically read them and project them in the digital twin. And I show you now what I mean with this with an example. The most, difficult thing of this type of models is that typically you have a large amount of data, so terabyte of data, especially if you read continuously the data. So you need to use artificial intelligence to select the data that are meaningful for your analysis. And you were before mentioning the fact that the future is going to be mixing artificial intelligence with this type of advanced model. So artificial intelligence can read the data, interpret the data, and basically give, it's like, just to give you an example, what you do typically, you have your heart rate. I measure your heart rate every day. Your heart rate changes every day, goes from high rate, low rate, it changes the average, peak, maximum, minimum, but it changes continuously. So it's impossible to tell you if you are sick just reading one data or one day. So we read for 3-4 months your signals. We use 300-400 features of your signals. You use artificial intelligence to basically classify these signals. And then we can tell you if you're sick, if something is changing to your heart rate, because something is changing, because there is a different trend, because there is a different feature that is changing. We do the same for bridges. So we measure a lot of features, and after 1 year, we can tell you if the performance of the bridge is changing. Also, you were mentioning the fact, it's true, with the sensor, you can model beyond the performance, beyond the serviceability limit state. So we can measure only basically the normal performance of the bridge, not the ultimate. But to do that, then to study the ultimate is very useful of the digital twin, the sensor, and I'm going to show you why with an example. These are 2 bridges, very important bridges in Italy that we are monitoring. We are monitoring them with artificial intelligence and also with digital twin. And we use Bayesian updating to update in real time the digital model with the sensors. This is and I go on directly, so I go back. Videos have, if they don't work, now these videos are, you need to click on the video, they should work. If you go up to the first one on the left, okay, this is a digital twin. So if you see on the left, there's a numerical model, and on the right, instead are the signals that are reading from we are reading from the sensors. So we read the sensors, we perform the operational model analysis, we get the frequency eigenmodes of the bridge, and we use a Bayesian updating to update also the numerical model in real time. So we know that basically the digital twin is exact replica of our bridge. And what do we do with this, going into the performance of the bridge? We run stochastic analysis on the bridge, and we can tell you what happens on the bridge in the next 50 years. Or we run extreme events to see what is the performance of the bridge beyond, obviously, what is the serviceability limit state. And this is just an example of a railway bridge. You see here is the wind that is reading, and now there is basically the train that is going by. This is a wind reading the sensors, and then like you will see also the bridge. Why is it important? Think about that. If we have it synchronized, it means that we can performance out of analysis with this model to see, for example, fatigue problem with the bridge. Or we can run earthquakes, okay, and simulate the earthquake and see what is the probable damage on the bridge. And then maybe also train the bridge, train the artificial intelligence with this model to be able to also, instead in this case, study the bridge at the ultimate state, so for extreme events. So these are the stochastic, and this is what we do typically. So we have the bridge, we run several time history analysis, we see what is the behavior of the bridge, we classify the damage, and then we use artificial intelligence to train what is the model that we need to use then, for the structure. And we use also after extreme events, obviously, when it's calibrated, to see the performance. So you have the signal at the base, you have the sensors on the top of the bridge. Just after the event, you can see the performance of the bridge. All these models are non-linear, so we can also model, obviously, what is beyond the service limit state. So what is only, I close my talk. So yeah, we have these tools, and I think we are more advanced than we think. Like sometimes we have a lot of data. We have finite elements models that are extremely performing. We have now algorithms for artificial intelligence that they are really effective. What is missing and what is going to be difficult is to train the practitioners to use these tools, to train even the researchers to use these tools. And also another thing that I notice, that often people rely too much on artificial intelligence. This happens, for example, in Italy, is a trend. So you have people that are analyzing bridge that are not even bridge engineers, because they rely on the data just coming from the artificial intelligence. But we always have to remember that instead is a mechanical behavior that we need to interpret. So we can use artificial intelligence as a tool, but we need to be able also to interpret the data as an engineer. That's very important, because otherwise it's completely unuseful to use these tools. Thank you.
Thank you very much. Thank you very much. Well, I think we got almost to the end of this. What I would very much like to invite all of you, please, to come here or from there, and I will ask you three things. I apologize. The objective of these things was very biased to the things that we will very much like to hear. And I detected three things that for which I didn't get enough information, and I would consider it very important. So it would be, for me, a good opportunity to ask you three things. The first one is, what should we do to educate our future engineers so that the aims expressed in this panel are fulfilled? The second one, what should we do about risk communication? Risk communication is the most important thing, I consider myself, as we should not forget that disasters are not natural, they are man-made. And many of the things unexpected after, say, a big earthquake, are a consequence that we didn't know the risk. We were not prepared for that. And when we said we as society, communities. The other one, I noticed that the emphasis of all presentations have been in the structures, buildings, bridges, and not stressing the fact that the problems of earthquake engineering are multidisciplinary. We didn't talk about critical infrastructure. We didn't talk about lifelines. I wonder how we can guarantee a recovery time for a structure if there is no water, or how we can guarantee water if a pumping station building collapses. And that's just to give a small example. We got to have a more global view of what the aims of earthquake engineering are, if we think, of course, in communities, not only in the piece of infrastructure. Finally, one of the things that for me still puzzles me is that when we talk about resilience, we talk about functionality recovery. Functionality. And we never talk about operability. Operability is an issue. Say, for instance, again, I go to one of the things I did, water system. A water system that is very damaged, and it will take perhaps months, even years to be repaired. But what we cannot stop having is water. And that's also a problem of earthquake engineering. What should we do to be prepared for that? How are we going to operate the system so that we recover this operability and the benefit of those affected? I think I leave you that to think about, and I would very much, if you have anything to tell us later, to put it in pencil and paper, and we will communicate it to the people. As a research educator, yeah, because my aim is educate people through my research work. I think I insist, what should we do to prepare our young students to do what we are aiming here? Those that are here will not be there, yeah? But we want to leave that question to you. What should we do to educate our peoples so that they do the things we got to forget after seeing all these tools that were mentioned here? What should we do so that we don't have any immediate experience, yeah? Immediate experience that these young people get because they know how to handle the mouse of a program, but they don't know the meaning of what they're doing. Methods are of very high technology. If we keep with an education that we have currently, there are too many risks associated to the use of these tools. That takes us again to simpler models. Simpler, we cannot change the way the practitioners do their work. Let's give them the information so that they use it the right way. And having said that, and I really would like to thank you in the name of my institute and the personnel, and of course, not leaving to thank Luis Esteva to be with us and to share this opportunity with us. Luis, thank you very much, and thank you very much for everybody. Comes con nosotros, vamos a comer. ¿Quieres comer con nosotros? En el restaurante aquí arriba, no sé, nomás una escalera, ¿sí? No, ahorita arreglamos cómo te mueves, ¿sí? Ahorita arreglamos cómo te mueves. Khalid. Please. Arturo, Mario. Call please that we meet in the restaurant just around here.
Okay.
Yeah?
So yeah, I was just going to go to the restaurant.
Yeah, all right. You give all right. Yeah. ¿Se come con nosotros, Arturo? Sí. Sí, aquí arriba. Sí, come con nosotros aquí arriba. Ah, ya, sí, cierto. Bueno, a la próxima. Sí, linda. Ah, ¿cómo no? Sí, pues ahí, secuéstrelos. Cuidado, no se me vaya a caer, no se me vaya a caer.
Pero no se vaya.
Ándale, gracias. So they want to ask you some questions outside. Yeah, all right.
¿Una foto?
Ah, sí, una foto. Don Alex, una foto aquí, Artur.
Foto.
Okay. What you raised at the end is like the most important one. We need a civil engineer in Berkeley, what they, to deal with this, they created what they call a systems program. So then you have to deal with these things, a system of systems.
Yeah.
That's the only way.
Yeah, yeah.
In the middle.